we discussed that this was not following normal distribution, this is following normal distribution. So what is this normality? So normality is like most of the observations, whatever we take in our daily life, it clusters the large values, and most of the values, it clusters around a peak. Okay, so this peak, and if you take the other values, the probabilities of the other values, it starts decreasing on both the sides. So that's how we call as a normal curve is a bell-shaped curve, which you must have read during your undergraduate period, or maybe now when you are analyzing things. So that bell-shaped curve is the normal phenomena which has been seen with most of the variable when we plot a graph of those variable, those frequency. So that's the normal distribution, and that's the normality. That means the data which we have taken, that is behaving like a population data, right? Because day one we discussed that why we are doing research. So there we discussed two types of statistics. There was a descriptive statistics and there was a inferential statistics. Most of us are involved in the inferential statistics when we are estimating the population mean, taking a sample from that population, right? So checking the normality of that sample is very important, because if the sample is also following a normal distribution, that means it is mimicking the population. It is very much similar to the population. So whatever we are predicting, that will be near normal, near accuracy to the population value. Did you get it? Why we have a normal, why we check the normality of a data? Because we are trying to estimate a population parameter, and because if the data, because in population, if you take a large value of any variable and if you plot a graph, it follows a distribution where most of the values, it lies on the peak in the central, and then it starts decreasing to the periphery, both the right and left side. So that's how we want to test that if the data is normally distributed, our data, the sample data, because you have seen that there are 1,000 number and we are taking few numbers from that population. That means there is a less chances, there is no chances of sampling error, and whatever we are predicting, that is near to the population parameter. Okay, so now you can am I audible to all of you? So now you can see that this is a graph of a 14-year-old girls, where you can see the mean is 1.51, the height of the girls, it is in the meter, and standard deviation is 0.074. One rule of following or estimating this normality, that if the mean of, if the standard deviation of that data is less than the half of the mean, it is generally normally distributed. That is one of the objective criteria for deciding whether the data is normally distributed or not. So if the standard deviation is less than 50% of the mean of that data, that means that data is normally distributed. And you can see the bell-shaped curve here, that it is showing a normal distribution, the height of a girl's 14-year-old girl. Now the second is the, you can see here that there are two graph, there are two bell-shaped curve, and it is showing that they are having a different means, but the standard deviation is same in both the case. The case of the first mean value is 100 and the second has got a mean of 150. So they have got a different mean, but the standard deviation is same. You can see this third one where the mean is different. You can see the mean is same in both the cases. It is 100, but the standard deviation is different. In the first case, it is 15 and the second one is 30. So the larger the standard deviation, the spread of the curve will be wide. So this is the general concept of a standard deviation and mean. Now we call it as a normal distribution. So any two groups of the data, like we'll be doing in the independent sample t-test. So if you are measuring something, any outcome variable across the two groups, then both the groups should be normally distributed. And in this case, you can see by the graph that there is a normal distribution, because both the graphs are the bell shape following the normal distribution. But just focus on the second one. You can see here that the 1 is anomaly, that the maybe if the dependent variable is the engagement scores, then the males are following a normal distribution, whereas the females, they are following a skewed deviation. So in this case, there are ways to handle the skew deviation. Like one of the ways, data transformation, which we will not be telling you in this session. So there are 2 ways to test for this normality. There is a numerical method and there is a graphical method. So first we will focus on the numerical method. So numerical method of normality testing, it is a bit objective because you have a value. So you can definitely tell whether this is normal or not normal, right? The other is the graphical method. Graphical method is more of a subjective in nature because you have to see the graph, you have to interpret and analyze it. So you need a little bit of more experience in analyzing the graphical method, but both has its own pros and cons. The numerical method, it is very sensitive for low sample size. Means if the sample is low, you should go for the numerical method of testing the normality. There are one way I told you regarding the mean. If the standard deviation is less than 50% of the mean, it follows a normal distribution. The second is the skewness of the data. So you can measure the skewness and kurtosis of the data. And the third is the Shapiro-Wilk test. So we will discuss about all these 3 one by one. I have just about these things in detail. So there are 3 ways of measurement. So there are 3 ways of measuring the normality of data using a numerical method.
Voice break again.
Yes, that we are also feeling this problem today. And I think I'll repeat because there is some internet unstable connection. It is showing many a times, maybe because of heavy rains. We will also having a talk with the IT department of AIIMS. So we hope to resolve this soon, but till that time, keep on texting in the chat box so that I will repeat the content if there is a break in the voice. So I think, should I start again with the normality?
Now the voice is clear, ma'am.
Okay, so there are 2 ways to test for normality. There is a objective way and there is a subjective way. Objective way is a numerical method. Then there is a value and there is a cutoff. So you can decide whether it is a normal distribution or not normal distribution. Subjective ways are based on the graphical representation. So you need a little bit experience of interpretation of that graph to say that it is normally distributed or not normally distributed. So I'll first talk about the numerical method. Both methods has its own pros and cons. Generally, it is recommended that if the sample size is less than 50, you should use the numerical or objective method of assessment of normality. If the sample size is more than 50, then you should use the graphical method of assessment of normality. Is that right? Am I making sense to you? Again, I'll repeat. If the sample size is less than 50, we should use the numerical method or objective method of assessment of normality. If the sample size is more than 50, we should use the graphical method, which is a subjective method for the assessment of normality. So now let's talk about this one by one. This objective method of assessment is sensitive for low sample size. I have discussed that. And there are 3 ways for assessment of normality. The first is the skewness, second is kurtosis, and the third is the Shapiro-Wilk test. We will discuss this one by one. And if I talk about the graphical method, it is applicable for sample size more than 50, and it is done by, there is a known as the QQ plot. So quantile plot or histogram. So there are 2 ways for assessment of subjective way of assessment of normality. So now, how to do this? That we will discuss is there is an explore button. I'll come again this thing. So if I come to the Shapiro-Wilk test, in the objective method, we saw that there were 3 tests. So Shapiro-Wilk test is one of a very good objective way to determine your data is not normal or normal. So the first important point is that the null hypothesis of this Shapiro-Wilk test is that the data is normally distributed. So what will we desire? That we always reject the null hypothesis, right? So so what is my wish? That my null hypothesis should be rejected because I mean, in this case, my null hypothesis should be accepted. And for that, because if my null hypothesis will be rejected, then my p-value will be less than 0.05. So in this case, the p-value is, if it is more than 0.05, then it is good for me. Generally, we always want the p-value to be less than 0.05. But since the null hypothesis says that the data is normally distributed, I want my null hypothesis to be accepted. Yes, I want my data to be normally distributed. That's why I don't want my p-value to be less than 0.05. So here, when the p-value of a Shapiro-Wilk test, if it is more than 0.05, the data is normally distributed. And it is more suitable for sample size less than 50. And generally, we test this across a group, but you can test it on a single data set also. But generally, we use Shapiro-Wilk test for testing the data continuous variable across 2 or 3 groups. So is it clear to all of you the Shapiro-Wilk test? I'm only telling you the theory. We will discuss the commands on SPSS and will interpret once again. So Shapiro-Wilk test, the desirable thing is that the data should be less than 50, the number of the data, and we want p-value to be more than 0.05, right? Now the second is the skewness. So skewness is the deviation from the normal. So what is a skewness? It is a symmetry of the curve.
Ma'am,
you see the normal curve, you can see that the 50% of the data. So now coming to the skewness.
What is happening? जब link break हो रहा है, तो whatever is saying that is in network and then suddenly coming very fast. Now it's okay.
So am I audible in a normal manner to all of you? Because there is some problem going on with this internet connectivity, and I think that's why there's a little bit of problem in interpreting and hearing. Switch.
Start the skewness part again, ma'am. The voice broke.
Yes. Okay. Skewness. I was telling about the skewness. That skewness measures the symmetry of the graph, right? So if you see the normal bell-shaped graph, 50% of the data is right of that peak and 50% is left of that peak. So it is a symmetrical curve. But if there is a deviation from that, it will be measured by the skewness, and it is the tail of the curve which tells us about the skewness. There can be a right skew or there can be a left skew. That we'll see. And for data to be normally distributed, the value of the skewness should be within ±2. Is that okay? So we talked about the Shapiro-Wilk test, where we said that we want the value to be more than 0.05, then only the data will be normally distributed, and it is applicable for sample size less than 50. For skewness, it measures a symmetry, and if the value of that skewness is within ±2, then it is a normally distributed data, because I said that this is a objective way or a numerical way of testing the normality. So you have got a value. If the value is less than that, it is normal. If the value is more than that, it is abnormal, not normal. We call it not normal. We don't call it abnormal. And then about the kurtosis. So kurtosis is basically, it measures the peakedness of the graph. Peakedness means height of the graph. So actually, if there are more peak or less peak than the normal distribution, it is known as not normally distributed. It can be leptokurtic when it is at more peak. It can be platykurtic when it is less peak. You don't need to go into the detail of these terms. Please don't get apprehensive about these terms. You don't need to remember even this. Just remember that the value should be within plus minus 2. Otherwise, most of the time we use the Shapiro-Wilk test and QQ plot to test the normality. In all the data set, we don't need to apply all the ways of normality. Okay, we have talked about 3 numerical method and 2 graphical. So there are mostly 5 ways to assess normality, but you don't need to test your data for all the 5 ways. Generally, I told you regarding the sample size, if it is 50, less than 50, then most commonly used test is the Shapiro-Wilk. If it is more than 50, most commonly used test is the QQ plot. So just for theory, I am telling you, but for all practical purposes, we will focus ourselves on the QQ plot and Shapiro-Wilk test. So again, the value is same. So this is just to show you that the positive and negative skewness and positive and negative kurtosis. So another way to do is by the histogram. And in histogram, I'll show you there is a option where you can click that and it will come. So normal QQ plot, the full form of QQ is quantile plot. And it is the best, one of the best method of assessing normality graphically. And if the data is normally distributed, the circular dots will be positioned along the diagonal line that we will see. So you can see this is a normal QQ plot. You can see that the data, the individual dots that is lying across the line. And this is again a QQ plot of a female. And you can see here that it is also normally distributed because most of the data is aligned diagonally across on that line or very near to that line. So this is the type of skewness you can see here. It is not lying on that line. And this is again a skewness. This is kurtosis and this is again a kurtosis. So this is comparing the histogram with the QQ plot. Both are showing you the way histogram will show the data and the way it will appear on the QQ plot. Is that okay with you? I will show you these commands once we go with the independent sample t-test. So any query till this point in the theory, I have not told you anything, any command till now. Okay. So now starting with the independent sample t-test and one independent sample t-test. So what would be the research question? So just see these research questions. Is the new teaching method, like one researcher has adopted a new teaching method which can improve the overall mean marks. So is the new teaching method can improve the mean marks obtained compared to the institute mean marks. So if like I want to do a study and I want to see the what is the mean of the marks obtained in the main professional exam, and
voice is cracking a bit.
Hello, ma'am.
Okay, I'll again repeat these research questions.
No issues,
Yes,
but
yes.
it's quite clear. It's
Can
Now it's clear,
Okay.
ma'am. Now it's clear.
Okay. In between, it will happen. So I will just wait for a few seconds to be normalized, and then again I'll repeat the slide. Even if it was missed or you couldn't hear anything, so I'll repeat the entire content. Don't worry. So the first research question is, I have started a new teaching technique, and I want to see if after this new teaching technique is the mean marks of the whole class, it is better than the institute mean marks. Institute mean marks means what is the average mean of the that batch, the whole institute. If I want to have a value, then I can compare. The second research question is the hemoglobin, if I have taken a sample of pregnant women, maybe if Dr. Mukta is doing some survey in the gynecology department, and if she takes the mean of 400 or 500 antenatal women, and if she wants to compare that mean hemoglobin level to the national average, like what is the national average of hemoglobin, then this is one type of research question. And then the third could be, is there any difference between the depression level which are in my sample and the depression level in the population? So depression level means it will be measured in score. It will not measured in the proportion. So if you can recall the one sample chi-square test, so this is again the same as one sample chi-square test. There the outcome variable was in the proportion, and here the outcome variable is in the terms of mean, continuous data, and that was a categorical data. So that is the difference. Otherwise, everything is same between a one sample t-test and a one sample chi-square test, because there also we have got either a known value or a hypothesized value. Here also we have got either a known value or a hypothesized value. So if you see these three research questions, what have you observed? That consistently in all these three research questions, there is a scale variable. All the three variables, whether it is a mean marks obtained by students, whether it is the depression level measured as a mean score, or whether it is hemoglobin level measured in gram per deciliter, all these three variables are continuous in nature. That means the measurement is the scale variable, and we want to compare it with the known average. That known could be hypothesized, or that known could be, there's already, we know the value. So what is the appropriate test for this? So appropriate statistical test would be whether there is any difference in average score of the scale variable as compared to a known or hypothesized population value. So the appropriate test here is the one sample t-test or single parameter t-test. This is also known as the single parameter t-test. So one sample t-test, the alternate name is single sample t-test or single parameter t-test. So there are only three underlying assumptions of this t-test. The first assumption is that there is only one dependent variable which is measured on a continuous scale or a scale variable that we have discussed. The second assumption is that variable should be approximately normally distributed. Here I am writing approximately normally distributed. And what do I mean by this approximately? Why I am not writing that variable should be normally distributed? That we'll see once we give the command. Because this t-test is a robust t-test, and slight deviations for normality, it doesn't affect the t-test. So even if there is a slight deviation, you can still apply this t-test and the results will be applicable. So that's why we write it approximately normally distributed. And the third assumption is there should be no significant outlier. This is also important because we cannot say that there will be no outlier. The generally is if there are a few outliers, but they are not very significant. So all these three assumptions we will check before we apply the test. So just a few concepts about outlier. These are the three box plot which you can see here. The box plot tells you about the outlier. So in the first box plot, you can see that the male and female distribution is there. You will check this on SPSS also, systolic blood pressure, and you can see that in the first diagram, there is no outlier. In the second one, there are few points you can see here. So what is there? That outlier, generally it is of two types. There is a normal outlier and there is a extreme outlier. So how do we define an outlier? If the data point that is more than 1.5 box length from the edge of their box, so that 1.5 will be from this edge. So if the data point is like, you can see the data point 10, 23. So these 2 points are more than 1.5 box length from the edge of this box plot. They are known as the outlier. The second condition is about the extreme outlier. If a data point, and this normal outlier, it is shown by a circle or a dot, circular dot like this, you can see here. The second type of outlier is an extreme outlier. So a data point which is more than 3 box plot length from the edge of this box plot, this is known as the extreme outlier. And here you can see it is shown by the asterisk. So this 173 is an extreme outlier. You can see the data here. So you can see, can you tell me which number is an extreme outlier here? Or you can type in the chat box also. In third this box plot, which are the case number? These are the serial number or patient ID number. Okay, so you are just let me go through that chat. $160, 38, 23 is correct. Yes, 14. Where is 14? Yes, 14 is correct. 18, 160. Yes. So you got 122 and 23. Yes, you are right. So you know now what is the concept of extreme outlier and what is the concept of normal outlier. So did you get this? Okay, and please remember that these are not the values, because one of our students got confused with this number as value. So this 160 is what? Is this the value of SGOT?
No. Case number, serial
What
number
is
of
this
the patient.
160? Can anyone explain?
Serial
Yes,
number of the
yes,
patient.
Yes, Dr. Mukta, rightly said. So this is the serial number of the patient ID number, whatever you have defined in your data sheet. This is not the value of SGOT, right? So don't go and search for these value. Yes, Nilima is writing what is 3 box plot or 1.5. So, you know, Nilima, you know, overall this box plot is this much. Can you
Voice break.
see?
Can you
So
repeat it,
if
ma'am?
so you can see here, you can see the normal height of the box plot, right? Let me come. Where is my mouse? Yes, it has come again. So this is the normal length of the box plot from this to this, right? So if the data, it is more than 1.5 box plot, and this, the SPSS does this in background, that if it is, because this length of the box plot says that that data has come into it, but that data is lying outside. So the SPSS defines that data as an outlier. So if the data is outside, the value of that data, 1.5 means total 1 and add half of it. So this 110, if you measure the distance here, not exactly the distance by a scale or something, but in the background, if you take this 10 value will be more than this plus 0.5. So this is more than from the edge of this box plot, right? From the edge of this box plot, the value of this will be more than 1.5 length. So this is the outlier. Whereas if you consider this 173, it will be more than 3 box plot length from the edge of box plot. So that's the way the SPSS decides about the data, where it is whether it is an extreme outlier or whether it is a normal outlier. Is my voice again breaking?
No, ma'am. Now it's clear, ma'am.
Okay, so Manisha, who asked this? Did you understand? Let me see who has asked this. Chat.
Nilima, Dr. Nilima.
Yes, Nilima, did you get this? She's not, I'm not able to hear your voice, Nilima. Okay, Nilima, thank you. So now any problem till this point? Then I'll repeat the concept once again. Otherwise, we will move forward. So if it is yes from your side, one of you can write yes in the text box, because there's a voice break and a lot of problems are going on. Okay, so Dr. Nishant is writing yes. So we may go ahead. Thank you, Manoja, Shivgami. Thanks to all of you. So now I'll go ahead. No, this is stuck up. So now there are various reasons for outlier. So basically there are 3 reasons for outlier. There can be a data entry error, there can be a measurement error, or this can be a genuinely unusual values. So there are ways to handle this data, this outlier. So what I told, data entry error means you have given this data, your hard copy to someone, and by mistake he has entered the data, normally large value or abnormally low values. The second could be measurement error. The tool which you are using is not sensitive. Any problem? The tool which you are using, is that sensitive enough, or that some problem goes with that tool? Like many a times in lab it happens that if there is a change of reagent, or there is a that calibration has not been done properly, the values comes abnormally large or abnormally low. We often face this problem, especially the clinicians. So that there could be a measurement error, maybe due to the not calibrating, or due to some change in reagent, or some change in person who does this. So there could be measurement error, or genuinely that value is large, means it has measured the value correct and it is either a very high or a very low value. So now how to tackle this? So the first way to tackle this is, you can do 2 things. You can see whether these outliers are significant or not. So if your data is very large, like you have got more than 100 and you've got a few outliers like 4, 5 or 6, then it is not a significant outlier. There is not fixed number how to define this. So either you can do one thing, that if there are many outliers in your data, you can go for non-parametric test, and non-parametric analog is the Mann-Whitney test. Or we can modify this. This non-parametric is for the independent sample, and then you can modify this with one that is less extreme. That means you can see the next lower or next higher value, and then you can change this outlier. The third option is to transform the variable, and it is a log transformation. But generally we don't do that, because if your sample size is large enough, you can include this outlier and you can run the analysis. Then you can ask the question that if the t-test is a robust one and it doesn't get affected by few outliers, then why there is a need to check for the outlier? Yes, there is a need to check for the outlier, because if the outliers are very large number, then you need to do a parametric test. Or you should always report this outlier in your data analysis. That while you have put the normality testing, you have come with the 4 or 5 outliers, and you have to report that they were included in the analysis. So whatever decision you are taking, you should write that in your data analysis. If you have transformed the variable, you will write that you have done the data transformation. If you have modified the outlier, you have to write that. If you are applying man-Whitney, you have to write like that. So there are ways to do that, right? So, but again, I said that if your sample size is sufficiently large, there's no definition of sufficiently large sample size. But generally, if you have calculated the sample size based on some parameter, and if it is more than 100, you can say, but that's again an arbitrary way. There's no way to decide the adequate sample size except for sample size calculation. So if you have applied a correct statistical way of sample size calculation, and if you have that much sample with you, then you can go with the outliers and run the analysis. So are you people okay up till this point? Are you on the same page? Is my speed okay, or should I go a bit slow?
No, it's okay. Dr. Pragya, just one question. Is
Yes.
there any rule when should we go for non-parametric test and when should we include the outlier? Because in our practice, usually when we calculate this mortality and all, there are outliers in the mortality group. So
Actually, rule is, again, I said that it's up to you. It's up, as such, there is no guideline, but yes. Then the question comes, what is a significant outlier? So you can keep that if your sample size is 100, and if there are 10, if the sample size is small, then even the few outliers are significant. Like if you are handling with 30, 40 sample, then 5, 6 outlier will be significant. But if you are dealing with 200, 300, then 4, 5 or 10 will not be significant. So in that case, we do recommend that you may change the value, or you may do the data transformation, or you may go to the non-parametric. The only problem with non-parametric is that it gives you the meaning in terms of mean rank, maybe if the distribution is same, or median. So it is difficult for the general person to understand the concept of mean rank, because it will tell you that we'll do that in the later part. The concept of understanding the mean rank is a bit different. That's why generally we say that if your sample size is large enough, you should go with your parametric one. And if it is a 4 or 5 outlier, you can keep the outlier. Or there is another recommendation. You can keep the outlier and then run the analysis. Then you can remove the outlier and then run the analysis and then see the result. Did you get, Dr. Mukta?
yes.
Like if there are 6 outliers, like serial number 126, 13 and 17. There are 5 outliers in my data. I have got 2 options, which is the most common, which we do. You keep these outlier and run the analysis. See the value of T and significance and keep it aside. Then what you do, have another data sheet. I mean, just make a copy of that data sheet and delete those values, like 7, 17 of that particular variable, and then again rerun the analysis. And if it is coming significant, then you can write both the things, that you have deleted it and then also it was significant. Because outlier, I have told you there were 3 reasons for outlier. The first and second reason was a measurement error or some data entry error. But the third reason was it could be genuinely high in the population. Yes. So even if few outliers are there, if you remove them and rerun the analysis and it is coming significant, then you can, but the only, my point is that write whatever you are doing. Okay. You have to write a detailed description, because many a time what we just leave these processes in between. Like we do, just see the protocol of any biochemist. He writes the sample testing in a such detailed way. This much value, this will be done, this process and all. We have seen, if you write the OT steps, again, you go in very detail. This thing is done, that thing is done. Similarly, whatever you are doing the data analysis, write each and every step which you are doing, because that tells the reader or the reviewer that you have done your data analysis the way it should have been done, and you have not left any component. So no, writing all these things in your data analysis plan, nothing is right or wrong, because you are only interpreting your sample result. So the best is, if there are few outliers, again, that few depends on the number of your sample size. If the sample size is 20 or 30, 5 outlier is very large number. It is not less, because it is 1/5 of your total sample. But if a sample is 200 and 300 and 5-6 outlier doesn't carry a significant meaning, right? So you include that outlier, run the analysis, have the result, you remove the outlier, run the analysis and present your result. And in the write-up, you can go with this. Or if you are feeling lazy enough not to remove and rerun, then at least you can commit that there were 5 outliers, but they were not extreme outliers. So I have included that in my analysis. So both ways you can do, both is acceptable. Once you go higher in analysis, then you can do these steps. If you are starting with the basic one, you can keep the outlier and run the analysis. Is it okay to everyone? How to deal with the outlier?
Yes.
Because we do recommend to go for parametric. That's why, again, I'm emphasizing, that's why we emphasize more on the sample size. Because, if your sample size is adequate enough, then this doesn't get affected, this few outliers. But yes, if there is a case study, something, if you are not able to get many times if you are doing some study from record, or if because of COVID or anything, if we are not able to get that much sample, then definitely, then in that case, you should go for non-parametric method. Again, there are ways you can express the result in median, because then there is no other way. Then how that result will be generalized? Because our basic aim that we should be able to generalize the finding of our sample statistics. That's our overall aim. So if we are not fulfilling that aim, the purpose of our research will not be met. I hope I'm clear. If not, then one of you please, few of you may ask questions, and then I'll go ahead with this. Let me see the chat.
What is the meaning?
What is the meaning of? Okay, so Mayuri is writing what is the meaning. Yes, we transform these data into a rank. We do the log transformation. So what this log transformation does, it gives these value as a rank. It takes the log of that value, and that removes the extreme values. Means it converts the extreme value into the less extreme. So that's the log, that's the value of transformation. That's done by the log transformation, which we are not telling you here. Maybe in advanced SPSS course, we will tell you about the log transformation. And that is not a very common way to deal with the outlier. If there are many outliers that we need to do a log transformation, that says that there was some problem with the sampling. Either it was too purposive or it was too convenient. Is that okay, Mayuri?
Yes, ma'am.
Okay. Should I move forward? And in that, Z transformation is also done along with log transformation. Like you must have seen many WHO that growth chart, and where we see the Z scores of various standard means various results. So that Z score is also one of the way of transforming that data. So either you can do it by Z score, or you can do it by the log transformation. So if everyone is okay, I'm moving ahead. Let me see the chat box. Any other question? Okay, so there is no question. So now we'll learn little about the hypothesis. So we always form a null hypothesis and an alternative hypothesis. So in this case, the null hypothesis will be the population mean is equal to the population known mean. So here the population mean is not the mean. In fact, it is estimated from the sample mean. It is equal as a known and then the alternate hypothesis is that the population mean is not equal to the known population mean. So this is null and alternate hypothesis. So now we'll go to the data. These are the commands. So we will go to the data set. This is our data set. I'll briefly explain the data. So you can see now today this has been converted, this role has been converted into none. So you can see the name of the variable, the type of the variable, all the variables are numeric in nature. Width, okay, there are variable with 12 and 8, and then decimal, all is 0. Maybe all we are taking it whole number, except this total protein, which is showing 2 decimal point. Label is there with all the variable, and you can see there are few categorical or a nominal variable and few scale variable. So gender, you can see the coding 1 and 2, 1 is for female and 2 is for male. You can see the race, it is same as yesterday's, day before yesterday's coding, white, black and others. Then you can see the socioeconomic status, it is again the same as previous. Then the BMI cat is also same as previous. And then you can see the MI order, first MI and the recurrent MI, this is also the same. The other things, SBP is the systolic blood pressure, DBP is the diastolic blood pressure, TP stands for total protein, SGOT is normal SGOT, sodium is sodium level, potassium, LDH and cholesterol. So these are self-explanatory. So that's why that's in short form is written here also. So this is the data sheet, and if I come to the data view, so this is the data view. You can see all the this thing is the whole number except the total protein, because we have fixed that up to 2 decimal point. Otherwise everything is in whole number. So that's the data. Now coming to the question. So the first question is you want to study whether the mean systolic blood pressure of your sample population is different from population mean, right? So first is I have to see that the mean SBP of my sample, is it equal to the mean SBP of my district? And the known value of my district SBP is 120 millimeter of mercury. So this is my research question. And the second is the mean SBP of my state is 140. So I want to check whether my sample mean of SBP, is it equal to my district mean or not, or is it equal to my state mean or not? And the known value of both this district and state is 120 millimeter of mercury and 140 millimeter of mercury, right? So what I'll do, I'll straight away go to the data sheet. So first I have to meet the assumption of normality and the underlying assumption. So the first assumption was my data should be a continuous variable on scale variable. So this systolic blood pressure is a continuous variable measured in scale. So first assumption is met. Second assumption is it should be approximately normally distributed. So for that I need to, and the second was the third was the outlier. So for the approximately normally distributed, there is an option in the descriptive statistics of explore. So please remember this command, and from now onwards, we'll keep on putting this command explore. So come to the descriptive, explore, click on that. Here you will see three boxes rather, dependent and factor. Here there is only single variable, so I'll move that variable, and that variable is a SBP to the dependent list. Here I'm interested in plots because I told that it is a plot which is important. So here, upon clicking that plot, uncheck this and check this normality plot with tests. It tells you the most common, this is the most common way we check for the normality, and it gives you the box plot as well as QQ plot, and again the Shapiro-Wilk value, which we have seen. So press this continue, press this OK, wait for a few seconds, and this comes. So you can see here, there is a 193 total case, then test of normality. So you can see here, what is the value? So value of this Shapiro-Wilk is, what is the significant value? It is 0.166. So we discussed that we don't want this value to be significant. We want p-value to be more than 0.05, and this is 0.05. So data is normally distributed. But since this is a sample size which is more than 50, so it is not desirable to use this value of Shapiro-Wilk. Rather, what I'll use, I will use the QQ plot. So if you go down and if you see this, you can see that most of this is the across this oblique line. Can you see this? Most of these values, this is across this line. So it tells you that the systolic blood pressure is normally distributed. So this is the QQ plot, quantile plot, which is a graphical method or a subjective method of assessment of normality. And if the values are distributed across the diagonal line, that shows that it is normally distributed. Don't concentrate along these few values which are not on. It will not be exactly on that line. Rather, it will be very much near to that line, and also the majority of the values. So you can see the more tightly packed these circles are, that shows you that most of the values are the normally distributed value. So you can say that the data is normally distributed, and then you can see the box plot. Here, can you see any outlier here in the box plot? You can write in the chat box, so you can unmute.
No,
Okay, yes, very right. So we cannot see any outlier here. So we have tested for all the three assumptions. The data is continuous in nature, it is normally distributed, and there is no significant outlier. So now, since this all the three assumptions has met, so now I can apply the test. So what I'll do, I'll go to analyze, compare means. So from now onwards, for today, not now. So today we'll use only this command, because today we'll be comparing means mostly, except for man with me. So where we'll compare median. So compare means, then I'll click one sample t-test. So it is a one sample t-test. So test variable is systolic blood pressure. So I'll click this and I'll move this here. And I don't have to do anything. Again, I have to write the value against a hypothesized. So my first hypothesized value was my district mean SBP, which was 120. And I'll click on this. Okay. So you will come up with the output, and you can see here that the mean of my sample, how much is the mean? So the mean of my sample is 143. Can you see? And hypothesized mean is 120. Standard deviation is 31.43. So again, if you see, we talked that if the standard deviation is less than half of the median, it is normally distributed, and definitely it is less than half of the mean. So this is the thing. So now if you see the systolic blood pressure, you can see here, what is a significant level? Yes, it is significant. So this, you have to report this. You have to report the value of T and the degree of freedom, and then you have to again report the mean difference. So the mean difference from the hypothesized value or the known value was 23, and it was significant because the confidence interval is from 19.40 to 28.33. And since we are testing the difference, so value of confidence interval, the value of 0 should not come in between. That day also Dr. Mukta was asking whether it should, 1 should be there in between or 0 should be there in between. So in case of any difference, so we are calculating the 95% confidence interval for the difference. So that's why difference value of 0 should not come in between. So this is a significant p-value as shown by the significant two-tail and also by the lower and the higher value. So now how to interpret this? So if you go and how to enter this value in the table. So if you go and see this table, so this is the APA style table. Your table should start with the table number, the title of the table, and the sample size. So because we are comparing the mean SBP against a hypothesized value, which is 120. So SBP of my sample was 143.9 with a standard deviation of 31.4 and mean difference of 23.9. And you have to write the value of T, the degree of freedom, and the p-value. So one of you can read this
Values of SBP was normally distributed as reported in QQ plot to test the normality. A one sample t-test was applied to test whether the mean SBP of your samples differs from the district mean. We observed a statistically significant difference in the mean BP of the study sample from the hypothesized population. T-value 10.5, degree of freedom 192, p-value less than 0.0005.
Yes, actually here we are not telling the actual p-value because it is very less. It is 10 to the power, if you can go 0.00000, too many zeros, because you can see here in the output, day before yesterday, I told you that you should report actual t value. But when it is very, number of 0, you can, how to see the actual p value? What I told you that day, Rose, can you repeat?
You have to double click and see.
Yes, very good, very good. I have double clicked this, and if you see this, it is minus 21 e to the power minus 21, 21 0, and then that value, right? So you cannot, in this case, you cannot write the actual p value. So that's why we have written 0.005, right? So many a time when it is highly significant, then the number of zeros are so large that you cannot report the actual p-value. So in that case, nothing is left, and you have to write that it is less than 0.005, 001, or whatever, up till 3 decimal point. Okay. So that was the one. Now the second command was I have to test it against 140. So 140, what will I do? I'll go to analyze. Then I'll go to the compare means, one sample t-test. And again, what I need to do here, one of you, please guide me. Nilima, what should I change here?
Yes, ma'am. The test value.
Yes, very good.
140.
What did I write here?
140.
So I have written here 140. Then again, I'll click.
What if we write the value is in the range?
No, that cannot be range because you need to give the absolute value.
Okay.
Range, you cannot write a range there. You can take the mid, you can take the mean of lower and higher value, like lower plus higher divided by 2. That will give you the mean value. Okay, but you cannot take a range there.
Okay.
Okay, so this then you can see here. So what all will you report? You can see the mean is again 143. Standard deviation, it will be same. And can you see here about the significance?
Ma'am, the confidence interval lies 0.6 lower value and upper is 8.33.
Yes. So Yes, and it is also not significant.
Not
0.0.
significant because it less than greater than 0.005.
Okay. Yes, rightly said. So it is not significant. So now if you go to the interpretation part and see the table. This was the table. Again, we are writing. So the result, so you can read the Nilima, you can read the
Yes.
interpretation.
The values of systolic blood pressure was normally distributed as reported in QQ plot to test the normality. A one sample t-test was applied to test whether mean SBP of your sample differs from district mean. We observed difference in mean SBP of study sample and hypothesized population was not significant with t-value 1.70. Degree of freedom 192 and p-value is 0.089, which is greater than 0.005.
So here by mistake we have written district, which should have been state.
Yes, ma'am.
Or generally we write here by the visual inspection of QQ plot. You should always write here that was missed. Visual inspection of QQ plot. And in case you are reporting for this Shapiro-Wilk, you should write the p-value that it was greater than 0.05. But in this cases, for all exercise and demo sheet, our sample size is 193. So we'll be using the Shapiro. We'll not be using with Shapiro-Wilk. Rather, we'll be dealing with the QQ plot.
Dr. Pragya,
Yes, Dr. Nishant.
this visual inspection of QQ plot, how can you say suppose the data is my baby, so my baby will always appear to be beautifully normally distributed? Is there any method by which we can visually say that no, it is now looking like it is not normally distributed?
Actually, this normal distribution is not for a single case. This is about a group of sample. So a group of sample, yes, definitely. I was telling you, it depends on how many samples you have. If you have got less than 50 samples, I told you there are objective ways to assess that. Even if that maybe you are talking about one baby, if in a creche or if in a, maybe in a school, in a primary school, maybe there are special schools also. Okay, there are not only primary schools. So in the special schools also, there are many babies who are, if you testing the IQ, because you will test some outcome of your baby. Maybe it's the external beauty or it's the IQ level, it's the alertness. So there will be some dependent variable which you are going to test. So again, I said that it has got the objective and subjective way. So objective way is very clear cut. I told you, enter the data, see the kurtosis skewness, or you see the Shapiro-Wilk test values more than 0.05, it is normally distributed. If it is less than that, it is not normally distributed. If your sample is more than 50, you plot this QQ plot by this explore option, and then if it is lying across, because that line, diagonal line, tells you about it is normally distributed, and if your data is along that line, then it is normally distributed. So this is the only way to assess the normality. And in normality, we assess a group of sample, not a single unit.
Suppose how unfair is it to use the Shapiro-Wilk test for suppose a sample of 100 samples? Is it or we should not use it at all, because objective is always better than subjective.
For high sample, it will always show you significant. You see now, you just see it right now. I applied Shapiro-Wilk. It may show you significant, it may not show you significant, it will vary. But this will not vary. If you see the Shapiro-Wilk, I'll come to the output. You can see the Shapiro-Wilk. Here it is okay because it is not significant. But many times you will see that if I apply it across the group, it will come highly significant. Then if you use Shapiro-Wilk, what it will say? It will say that your data is not normally distributed, whereas your data is normally distributed. So the sensitivity of Shapiro-Wilk is only up till 50. Okay.
Okay. Yeah.
So that's why it is not fair. It is not unfair. We cannot say it unfair to use, but because in the same output, you get the QQ plot also. You don't have to click something else. That's why if you click on, like how you went, now you have gone to the analyze, descriptive, and then explore, right? So you can write here, like I have entered the SBP, total protein, SGOT, all my continuous, maybe sodium, just to show you. And then I go for this plots. You can click here histogram also, but that will also give you the same thing. I am only going with these two because that is the most commonly done. If I click this and click OK, then you can see. And as you see more QQ plot, you will become more expert in analyzing. So just see the value of Shapiro-Wilk. Only one is significant. I mean, according to this, only SBP is significant. Normally distributed. See the other four. All other are showing significant. That means your data is not normally distributed, right? But if you go down and if you see the value, here it will give you the two. I told you, you have to see the box plot as well as the QQ plot. Now you see the QQ plot. It is normally distributed. There's only one or few values. So we can call it, because we always say approximately. That's why I have written approximately normally distributed, because 100% normally distributed you cannot expect. So this is again the most of the values you can see here. So if you go by Shapiro-Wilk, so what will you comment, Dr. Nishant?
We comment that only the systolic one is normally distributed, rest of them are not normally distributed.
Yes. But whereas if you see the visual inspection of this, then you will see, you see this total protein, this is normally distributed, only one or few values. Again, you go down, right? So, and you can see the outlier also, no outlier. Yes, there is one outlier here, which is a normal, not the extreme one, case number 22. And there is one extreme also, 30. This is not normally distributed. Here, the value of Shapiro-Wilk, and this is not, because this is classically not normal, skewed one. Okay. So there may be instances when by Shapiro-Wilk and QQ, you will conclude the same, right? Like in first case, where the value of SBP was by visual inspection also, it was normally distributed, and the value of Shapiro-Wilk was also 0.166. So it was normally distributed. But there, and in this case also, by SGOT, by the visual inspection of QQ also showing not normal, and by value of Shapiro-Wilk is also showing not normal. But in two cases you have seen that it was normal, but value of Shapiro-Wilk was showing that it was not normal. So did you get that?
Yes, I got it. Thank you, ma'am.
Yeah, there may be discrepancy. Yes, there may be instances when both of these will tell you the same result. But generally, we don't do that, because if you write that you tested with Shapiro-Wilk, the reviewer will get back to you saying this, how could you use Shapiro-Wilk because your sample size is this much, right?
Yes, ma'am, understood. Thank you. Yeah.
So that's the, that's how you should use. And again, QQ plot you should not use in less than 50, because you will not be able to interpret that, because the values are very less. It will go a little, we don't have any sample now with less sample, so that I could have shown you that visual inspection will be a little bit difficult to interpret the beautifully, which you are seeing it with a larger sample size, right? Because to follow it in a diagonal manner also you need more points. So that's why objective test is less than 50, and SPSS has designed its software in such a way that it picks up and sensitive. for less for chaperone and more for QQ plot. I mean sample. I hope you have understood this.
Yes, yes, perfectly. Thank you.
Okay. Thank you. If any query up till this point, we can take them. Otherwise, we'll go to the breakout room for the one sample t-test and very important normality testing. I'll start with the independent sample t-test. So independent sample t-test, again, if you see the research question, the first research question could be, is the average body mass index value of a population with a history of cardiovascular disease is different from population without history of cardiovascular disease? The second question could be, if I want to compare the pain score on visual analog scale after surgical technique 1 versus surgical technique 2, or if I want to see that does the medical undergraduate who have a good quality of sleep score high in exam as compared to poor quality sleep. So these are the three research questions. So what have you observed in all these three research questions? That there is a scale variable, and the scale variable was either the pain score on VAS, the sleep quality in maybe number of hours, or the BMI of the people with history and without history of cardiovascular disease. So all these three variables are on scale variable, and I want to compare it across two categorical variable. In the first research question, the two categorical variable was with history of cardiovascular disease and without history of cardiovascular disease. The second categorical variable was surgical technique 1 versus surgical technique 2. And the third categorical variable was undergraduate student with a good quality of sleep and with a poor quality of sleep. And the scale variable in this case is marks scored in the exam. Okay, so dependent variable here is in the continuous scale, and independent variable is a categorical variable with the two category. So independent sample t-test, we measure the continuous variable across two category, and the appropriate statistical test would be to see any difference in the average score of a scale variable across a binomial variable. So yes, you are right. The choice of test for such type of research question is independent sample t-test, also known as the unpaired t-test. The alternative name of this independent sample t-test is student t-test, between subject t-test, and unpaired t-test. So again, like you saw in the one sample t-test, there are few underlying assumptions of this independent sample t-test also, but there are two more concepts which we will learn here that we will see, which is different from the one sample t-test. So the first assumption of this independent sample t-test is that there should be one dependent variable which should be measured on a continuous scale. And I hope all of you now understand what is a continuous scale. The second assumption is there should be one independent variable that consists of two categories, and the two categories should be independent groups, and it should be dichotomous, means it should have two categories. The third assumption is there should be independence of observation, and we have discussed that if there are two separate groups, then this independence of observation criteria is met, because if somebody is there in the one group, he cannot be the participant in the another group. That is what we mean by the independence of observation. The fourth underlying assumption is that the dependent variable should be approximately normally distributed for each group of the independent variable. So in case of a one sample t-test, we tested this. We did not test the systolic blood pressure along any category, but here you will see that we test this across the independent variable. And there is one more assumption, that the homogeneity of variance should be equal. I will explain what about this homogeneity of variance. This says that the variance in both the group of the independent variable should be same. So this is again the same concept, and again that concept that there should not be any significant outlier. So that is not here, but that is the sixth assumption. So we have got the sixth assumption here, and the concept of outlier here also, it is just a repetition, that if the data point that is more than 1.5 box length from the edge of this box, this is classified as dot, and the extreme data point, if it is more than 3 box plot from the edge of length of the box plot, from the edge of the box plot, as it is shown by the asterisk. Again, we have seen about these reasons for outlier. So this is just a repetition of whatever you have seen. And now about the null hypothesis. So null hypothesis says that the population mean of the two groups are equal, and the alternative hypothesis says that the population mean of these two groups are not equal. So this is again the normality testing which we have seen about the sample size. When it is less than 50, we use Shapiro-Wilk test. When it is more than 50, we use QQ plot. So concept of normality is basically, we have discussed this, that the normality, the t-test, it is a robust test. So hence data should be approximately normally distributed. And if the sample size is more, then even if the data is not normal, it can be tested using t-test, because that says the central limit theorem. The central limit theorem states that the data, it follows a normal distribution if you increase the sample size. And if the distribution in both the group is in same direction, both positively or negatively, then you can apply this t-test. And if the direction of the skewness is different in both the group, then we need to check with the Mann-Whitney U-test. So this was the concept of normality. Now coming to the homogeneity of variance testing in SPSS. So homogeneity of variance tests whether the variance of the two population from where you have taken the two groups are equal or not. So it tests by a statistics known as the Levine's test of equality of variance, and it says that variance in both the population from where the samples have been selected should be equal. So now SPSS produced two types of independent T statistics. So this was about the Levine test of equality of variance. And again, like SPSS, where we have seen the Shapiro-Wilk test, the value of Levine test statistics should be more than 0.05, because the null hypothesis states that the variance of the two groups are equal. That's why we want the p-value to be more than 0.05. Then it will be said that the variance of the two groups, variance of the continuous variable, or just like SVP across the two groups, are same. So based on that, the SPSS produces two types of independent T statistics. The first is of equal variances assumed. In that case, we should use the standard independent T cell statistics, degree of freedom and p-value. If the Levine test of equality of variance not met, that means it is of unequal variance. And in that case, we should use the Welsh t-test statistics, degree of freedom and p-value. To repeat it once again, we test this Levine's test of equality of variance. SPSS statistics gives this value. If there is a equal variance assumed, or if there is the equal variance, then we will use a standard t-test. If there is unequal variance, then we'll use the Welsh t-test statistics. As an output, you have got both the statistics. We will see it how. So now this was the homogeneity of variance. I think I should, if you see this slide, so this comes as a descriptive also. If you click on descriptive, you can see the variance of male and female here. And by seeing this, you can see that the variance of the two groups are not equal. But this is not the way to test for equality of variance, because it tells you about the sample variance. Whereas we interested about the population from where the sample is withdrawn. That's why this variance will not tell you. There can be instances where the individual, if you compare the individual variances, they may or may not be the same. But you have to test with the Levine test of equality of variance, because that tests the two population variance from where you have withdrawn the sample. So basically in independent sample t-test, there are 3 research designs which are possible. The first is a mean difference between the 2 independent groups, which you have seen that there could be 2 groups of students, one with the good sleep and the other with the inadequate sleep. And then we can see the mean marks obtained in both the exams. There could be mean difference between the 2 interventions. There can be 2 interventions in the 2 groups, and then you can see what is the difference between these 2 interventions. And then in that case, you can see the mean difference in the change in score. So basically, these are the 3 study designs where we apply this. So now in the first case, you can see here that this is a first research question or study design where I want to compare the cholesterol level in male and female. So there are 2 categories of male and female of independent, and I want to see the cholesterol level in both these groups and to check whether there is a significant difference in these 2 groups or not. This could be one. The second could be the blood cholesterol level was measured after 6 weeks of exercise training program in intervention and control group. So there are 2 groups. One is the intervention group and other is the control group. Like we do in the randomized control trial, you are measuring something. So after that intervention, you measure the cholesterol level both in the control and in the intervention group, and you see whether there is a mean difference of these cholesterol value or not. This could be the second study design. Or you could do in the same group, you could do the pre and post, and then you can see the change in mean cholesterol level in both the group. But just to see the pre and post, for that you need to do a pair t-test. But here I am explaining that if you want to measure the change from the baseline, then you can use the independent sample t-test to see which group exhibited more change. Like you can see here, there is intervention group is one, and you can see that the intervention group is showing the pre-cholesterol, pre-intervention was 180 and post was 156. So you can see the difference. And similarly in the control, you can see the difference. So if I want to check where the mean difference of this group is significantly different from the mean difference of this group, then I may use the independent sample t-test. So these are the 3 study designs where the independent sample t-test is most commonly used. Now, this is the question whether you want to test that any difference in mean systolic blood pressure, mean diastolic blood pressure, and mean total protein of patients who have got the first episode of MI as compared to those who have a recurrent episode. So my objective would be to first check for the assumption. So I'll go to the data set. This is the question. So I'll start with the assumption. The first assumption was there should be one independent variable and there should be one dependent variable. The dependent variable should be continuous. So in this case, I have to test the systolic blood pressure, diastolic blood pressure, and total protein, which is a continuous variable. These 3 are the dependent variable. And independent variable is the order of MI. So order of an MI is the 2 stands for the second recurrent MI and 1 was for the first order MI. The same data set, I think it is the same. You can see, I think I have explained this data set also, so no need to re-explain this. So this was the two assumption. The third assumption was to check for the normality and any outlier. So for that, what I'll do, I'll go to analyze, descriptive, explore. So I'll click. So this I clicked initially. Now I have to see this against a factor, and that factor is your MI order. So against this MI order, I have to see the normality. So I'll click this plot. This is again clicked. I'll press this continue, press this OK, and then you can see here. So this is, if you see again the statistics, this. So you can see it gives you the normality of all the variable against these two categories, first and recurrent. So you can see these two are following normal distribution. This is not following the normal distribution. Again, this is not following normal. This is following normal. This is not following normal. This is not following normal. So, but again, what we concluded that we don't have to comment on Shapiro-Wilk because the sample size is larger than 50. So we'll see the normal QQ plot. So you have to see the normal QQ plot. So you can see here that QQ plot of the first order MI with the systolic blood, QQ plot of systolic blood pressure with first order MI, most of the values are along the diagonal line. So as visual inspection of QQ plot, it is normally distributed. Then if you see the recurrent order, it is also in the single line. So it is also normally distributed. Then you leave the other detrended one and then come to the box plot. In box plot, you can see that both the box plot of systolic blood pressure across the first and recurrent order MI, there is, can you see any outlier here?
No, ma'am.
Okay. So then coming to the diastolic blood pressure, you can see most of the values are along that line. Across first order MI, if you see the value of diastolic blood pressure along the, this recurrent MI, this is again visual inspection is showing the normal distribution. And if you come to the box plot, you can see that. So now can you comment, can anyone comment on this box plot? One of you can do this for me.
There is one outlier and one normal outlier and one extreme outlier.
In which group?
In first MI.
Yes. So you can write that the box plot of diastolic blood pressure with the first order MI has shown there were two outliers. One was extreme and one was normal, which was kept and for the analysis. That's the way you will write. Okay. And this 23 and 173 is what, Mayuri? Is this the value?
No, it's the serial number.
Okay. Okay. Thank you. So now if you see the total protein, so if you see the total protein, the MI order, first order, it is in the line. Then if you see the total protein here, again, anyone would like to comment on the box plot of total protein?
Current MI in total protein.
Aditi and Manoja, two of you. So one of you can explain the first order and the other can explain the recurrent order.
In first order MI, there is one outlier, that is serial number 30.
Okay.
Ma'am, in the recurrent MI, there are three normal outliers, 27, 158, and 22 serial number.
Okay, so if you get the same sort of data in your data sheet, you can again, we have discussed this in great detail, that it's up to you to decide. But since there are these are only very few outliers, so the decision to keep them in your data sheet is quite justified, and you can just write that you found one or two or three, just number of outlier, and you have decided to keep those outlier in your data, and you run the analysis with these outlier. So our basic aim in the data analysis should be to report for outlier. And then again, if there are many, then you can remove and rerun the analysis if the sample size is large. If the sample size is small, then even 6 to 7 outlier will carry an important role. In that case, you can run the non-parametric. So this is again the QQ plot of SGOT. So can anyone comment on the QQ plot of SGOT? What do you think from the visual inspection of box plot? This QQ plot, it is normally distributed or not normally distributed?
Kurtosis is there.
Yes, very right. And if you see the recurrent order again, the same thing. And if you see the box plot, can you see the box plot? So there are many outliers in both the cases. So in this case, it is not recommended to run a t-test. And in this case, you may, because there are many extreme outliers you can see here. And the QQ visual inspection of QQ plot is also showing that the data is not normal. So in this case, I would like to run a non-parametric test, the same which you'll see in Mann-Whitney U test, which is the non-parametric analog of the independent sample t-test. So I have tested for underlying assumptions. I have tested for independent variable and dependent variable. I have tested for outlier. I have tested for normality across the two groups. Now this value of Levine statistics, when you apply the independent sample t-test, then only you come to know whether the equality of variance is assumed or not assumed, because it gives you two values. How? We'll see. So again, after this has been assumed, I'll come. So I will click this comparison of mean independent sample t-test. So my aim was to see the test variable was to see. I'll press shift, select all these three variables, move them to this test variable. Now grouping variable here is the MI order. So I'll shift this MI order. Again, you have to define group. So 1 is the first order MI. So I have to write 1. Group 1 is 1 and group 2 is 2. So I may continue with this. In the options, you can, we generally express confidence interval as a 95% confidence interval. Leave this as such, no need to do anything, and then press OK. If you press OK, you can see there is a output where the first output will give you the mean value of that dependent variable, continuous variable across the two groups. Like you can see here, the mean of systolic blood pressure in the first order, you can see the total number. So it is the 133, the first order MI, and 60 is the recurrent order MI. And usually in your sample, there will be two unequal arms because the study design is such that there cannot be equal arms. But yes, if you are planning to take group equally, like intervention and control group, where you have seen that you are deliberately taking two groups, in that case, their group size will be equal. But since it is an internal grouping, so there are high chances that many a times you will find unequal group. But independent sample t-test is applicable in such case, and there's no problem, even if there is a huge difference in the group sizes, right? So don't worry about these group sizes, but you have to report this. You have to write this in a table. Again, you can see the mean value, first and recurrent order MI with the standard deviation of all these three. So now if I go down, now you can see there is this thing, Levine test of equality of variances. So you see one thing where the Levine test of equality of variances assumed, and second is the equality of variances not assumed. So in every column, you see there is a equality of variances assumed, and the second is the equality of variances not assumed. And you have to comment on the the significant value. So this significant value you can see in all the cases, it is more than 0.05. So that's why Levine of the test of equality of variance met. Since this is a very horizontally spread table, if I have to see, I'll have to drag this like this. So what I'll do, I'll double click this table and I may transpose the row. So what I'll do, I'll go to this, I'll double click this and I transpose these rows and column. So now the table which I have, it is not disappearing. Yes, so can you see now that table has been transposed? Whatever there was there initially as row, it has now come up to the column. Now this is compressed, so it is easy for me to see and analyze. Did you get what I did? Or should I repeat it once again?
Ma'am,
Repeat, ma'am.
Okay, yes, I just transpose the rows and columns. So like, what was the initial one? If you double click on table, initially it was like that. Initially, when I gave the output, the table was like that, right? It was in a horizontal spread. So I will have to drag this towards right side to see the lower and upper value and the mean difference for any value, right? So what I find it more easy if I transpose this and make it vertical. So what I did, I double clicked this, I went to this format option and transpose rows in column and then just click this. Then the table which you get, that horizontal is it's now coming in a vertical manner. So you, in one single view, you can see all these results. I have not told you about the interpretation, but just for the ease of interpretation, I have compressed the table from a horizontal spread to a vertical spread. Okay. Is it okay? Then I'll explain about the interpretation.
Yes, ma'am.
And the commands used, please repeat the commands used, ma'am.
Yes, it is the double click, pivot.
Not, ma'am, not for the transposition of rows and column, but for output, for getting this
So
output.
you go to that analyze, you go to compare means, you go to the independent sample t-test, you transfer the continuous variable, any variable. Right now I have transferred 3. If you want to test 10 variable, 6 variable, you transfer all the continuous variable here in this box. But this grouping variable, you can transfer only 1. So I want to see these variable across the order of MI. So I have transferred this order of MI here, and then there is an option of define group. So you go to this define group. Group 1, you press 1 because the first group is the first order MI. This is basically tells you about your coding. Whatever you have coded, so I have coded MI group 1 as 1 and recurrent MI as 2. So I have entered that number 1 and 2 here. You can do one thing. If your code is 0 and 1, you may transfer this as 0 and 1. But SPSS automatically takes group 1 as a lower code and group 2 as a higher code. So just in that case, if you have not coded your data, you may write the text. Like if somebody has asked the first very day that if they write male and female, and if they don't write code, what will happen? So nothing will happen. In that case, you have to enter in group 1 as female and group 2 as male. That's it. Except for logistic regression, because logistic takes the category as a numerical value. Otherwise, all this analysis, instead of number, you may write the variable as such which you have entered. But if you enter the variable, then again, it takes the result and table, it makes a little lengthy and heavy, but up to you. So did you get? Then again, I press this OK. And again, I press this OK. So that's the output which has again come up because I have again applied that command. So again, I'll double click this. So did you get, I think, the commands for independent sample t-test?
Yes, ma'am.
Okay. So then again, double click. I've gone into the pivot, transpose. I click this, close. Then only this becomes clear. Otherwise, that hazy appearance of table was appearing initially. So you can see here, there are 2 columns, right? So just see it very carefully. There are 2 columns for every continuous variable. Equal variances assumed and equal variances not assumed. You have to see the value of significance value of Levine test of equality. Can you see here? You can see that there is a Levine test of equality of variance, which tells you about the significance value. And if the value is more than 0.05, that means the equality of variance has been met. And it is same is the case with all the 3 independent, this dependent variable, continuous variable, that Levine equality of variances was assumed. That's why I'll take this value of T and confidence interval. If the value of Levine test of equality of variance, the significance value was less than 0.05, then I would have taken this column for my reporting of T value, degree of freedom, and significance. Did you get?
No, ma'am, please repeat. I didn't.
Okay. So while discussing the theory, we discussed that Levine test of equality of variance. What is a variance? Variance we have seen in the Mentimeter that variance is basically the difference of the 2 groups from the mean, from their mean value, right? So variance and normality, these 2 are different concepts. The data can be normally distributed, but the variance could be different in both the things. So that's why we are checking for normality and we are checking for variance also, right? Because in here you checked for normality by QQ plot, visual inspection of QQ plot. And this Levine test of equality of variance tells you about the population variance, population from where you have taken out these 2 samples, where the variances of those 2 population were same or not. So this is just to check whether the group which you have made, they are coming from the same population or not. Why? Because you have to, your main aim is to, tell about the population value. So in this case, the Levine test of equality of variance, you have to see its significant value. So if the p-value is more than 0.05, you have to take this box as your result for interpretation. Because here the equality of variance is assumed. If there is a case where the p-value is less than 0.05, then you have to take this column as a result, because here the equality of variance is not assumed. So in this case, in my case, all the three values, here the equality of variance is assumed, because here also the significant value is more than 0.05, and here also the significant value is more than 0.05. Okay. So by mistake that line appeared. Just a sec. So here also I'll take this as my value. Is it okay to all of you? Now, if I want to report this, so what I'll do? You can see the value of T here, the degree of freedom 191, significant is 0.01. Means the difference across these 2 group was significant. The mean difference was 11.72 with a confidence interval of 2.21 to 21.24. And this mean difference, you can see here, 11.72, it has come from the difference of these 2 values, 147.51 minus 135.71. Now, how to interpret this? So, and how to enter this result in the table? So you can see here, if I go down on this, so my aim was to check whether the systolic blood pressure of the SBP was same across the 2 groups. So this is a single table. If I have to make the single mean, so a table starts with a table number, a title of the table, and the sample size, which is missing. This table number is also missing, but you put when you are interpreting a table. This MI status first and recurrent, you can see this is the mean and this is the standard deviation. And this is a T value. This T value I have taken from this. Just a sec, I'll show you both in a single window. So can you see here? I have used the T value here 2.43 and the degree of freedom 191, significant 0.016, right? If the significant value, if this value of significance is 0.04, then what should I have used in T and degree of freedom and significance? Anyone?
2.483, 120 for degree of freedom, and significant value 0.014.
Yes. So had it been the case where significance was less than 0.05, then I would have used this column as a value of all of my interpretation: T value, degree of freedom, mean difference, and 95% CI. Although there is a little difference between these two, if you see in terms of values, but still you will use that you have used the since equality of variances was not assumed. So the T value and the degree of freedom and the mean difference was this. Is it okay to all of you which column we should use while interpreting the independent sample t-test, or should I repeat it once again before I go to the interpretation?
Yes.
Clear? Okay. So if it is clear, then there is a request that one of you can read this for me, this interpretation. Yes. Can anyone read this for me?
Yes. Ma'am, the values of systolic blood pressure across MI order was normally distributed as reported in QQ plot to test the normality, and independent sample t-test was applied to test whether mean SBP of patients with first order.
Yes.
With first order MI was different from patients with recurrent episodes of MI. We observed a statistically significant difference in mean SBP of patients having first episode of MI, 147.5 plus or minus 31.5, versus patients having second episode of MI, 135.7 plus or minus 29.8, with P equal to 0.016.
Okay, yes, thank you. So similarly, you can see, I'll show you with the output. So this was the output. If you see the diastolic blood pressure. So if I go down, so there's another one table which we have clubbed. So like you can write the comparison of mean SBP, DBP and total protein. So you can see here, I have written the mean plus minus standard deviation in first order. So you can see that I have taken this value 147, 81 and 6.8 from this table. And then again, the recurrent order, I'll take the second one. So 135, 69.4 and 6.750 plus minus their respective standard deviation. And you can enter simultaneously. You can open a Word file, and in one window, single window, you can open these two files so that you will not make any error while entering the result. And then again, here you can write because I have to enter the value of equality of variances assumed. So I'll focus on this. So 2.4, 191 and 0.01. And then again, you can write confidence interval also, which we have not written here. And then again, this 3.6, 191 and 000. And again, the similarly 1.1, this variances assumed where I have taken this as a difference, right? So you can see like total protein. So these are the differences, and these are the values which we have entered for an interpretation of independent sample t-test. And this is the interpretation. So this is, we have left this out because you can again write in the similar manner that mean value, their difference. And you can write that as shown in the table, the mean SBP and DBP differ significantly across first and recurrent order MI, while the total protein does not. Many a times journal, they say that you should not duplicate the result of, whatever it is evident in the table, you should not be writing in the text. So yes, in case of a thesis, you may write the same as it is seen in the table. But if you are submitting a paper for publication, generally you should write the interpretation, not exact value, because that has already been entered in the table. So this is the interpretation. I think yes.
Ma'am, how to correlate with the p value, because in the systolic blood pressure there was greater than less than 0.005, and I'm not able to get it.
This is significant. That means the difference which you are seeing here, it is significantly different across the two groups.
Okay.
I think is your question is something else? I didn't.
Once in one case we were using greater than 0.05 and less than 0.005.
Okay.
Therefore, I'm getting confused.
Okay, Nilima, that greater than we use only for Shapiro-Wilk and Levine test of equality of variance, not for t-test, or like I told you, here, let me check. Let me see. That greater than we use only in case we are testing equality of variance, right? Here, significant, you can see the significant level. This significance is not the significant level of this test statistics. There are two significant levels. One is the test statistics, that is the t-test, and the other is the Levine test statistics. Okay, assumptions, like you have seen the null hypothesis and the alternate hypothesis. So that is different for Levine test of equality of variance, and that is different for the independent sample t-test, right? So in case of Levine test of equality of variance, the null hypothesis says that the two variances are same, right? That's why significance of 0.05, if it is more than that, that is good sign for me, because I want my equality of variance to be same. It should be assumed, means variances are same across the two groups. Did you get?
Okay, ma'am. Yes, ma'am.
It is same like Shapiro-Wilk. There is just one, you can keep a wild guess, which often goes correct, that whatever comes with these fancy names, you will again see there is in ANOVA, there is a sphericity concept. So these test name with the fancy name like Shapiro-Wilk, Levine test, here we want p-value to be more than 0.05. Why? Because the null hypothesis is different than the test statistics hypothesis. Or if you don't, if you just want to remember that in case of Shapiro-Wilk and Levine test, you want p-value to be more than 0.05. Otherwise, everywhere else, you want p-value to be less than 0.05. And the underlying concept is the null hypothesis. Whatever, see, when we call null hypothesis, whenever we reject null hypothesis, then it is significant, right? When we accept null hypothesis, then it is alternate hypothesis, then it is significant. I don't know whether you have understood or not, because it is the basic concept of type 1 and type 2 error. I'm not going into the detail of that because that will again take more time. Just to remain focused and to understand, remember that generally we want our p-value to be less than 0.05, but in case of Levine test of variance and Shapiro-Wilk, we want our p-value to be more than 0.05, right? And it is just because of the assumption of null hypothesis. Null hypothesis is different in both these cases. That's why the desirable p-value is different for both these cases. Okay, Nilima?
Okay, ma'am.
Okay, anybody else who has got this difficulty in interpretation of this Levine test of equality of variance? If yes, please say it now.
Then in Shapiro-Wilk test and Levine's test, we assume that our null hypothesis is accepted.
Yes. We want our null hypothesis to be accepted because our null hypothesis is that the data is normally distributed. Our null hypothesis is that the equality of that the variance is same. So that's why I want my null hypothesis to be accepted. Whereas in case of other statistics, I want my alternate hypothesis to be accepted. Okay. Okay. So if it is okay, should we break for breakout room? I mean, should we go in the breakout room for the data analysis on our respective exercise sheet? Any other concept is there, then I may explain it right now. Just remember that when this significance value is more than 0.05, then you should use this column to report your result when the equality of variance is assumed in all the cases. Okay. So that's the, yes.
You had said about standard t-test and Welch t-set t-test. No, ma'am. Is this two columns? Is it that?
This is standard t-test, okay, and this is Welch t-test.
Okay, ma'am.
Welch t-test. I remember I've used in my PowerPoint a Welch t-test. So yes, this is a Welch t-test, W-E-L-C-H. Welch was a person who has invented this. So this was named after his invention, like all name tests which you see. So that's why this is known as the Welch t-test, and this is the standard t-test.
Okay, ma'am. Okay, ma'am. Thank you.
Okay. So the research question for a man with NEU. So this is again, the research question would be same as independent sample t-test, because since beginning, nobody wants to test median. Usually we want to test mean. But when the data is not normally distributed, or when there are a huge number of outliers, then we test the median values or the mean rank. So the research question would be the same as independent sample t-test. So the first research question could be, is the average body mass index value of population with history and without history of CVD will be the same. The second could be again the same. It is the same example which we have given you in the independent sample t-test, that comparison of pain score on visual analog scale after surgical technique 1 versus surgical technique 2. And the third one is, does the medical undergraduate student who have got good quality of sleep score high in exam as compared to poor quality sleep? So in this case, like initially, like I said, that we plan to compare the mean of all the variable, whether it is a BMI, whether it is a pain score, or whether it is an exam score across the two categories. But the variable of interest was not normally distributed across the two categories. That's why we plan to compare the median. So the median, so the modified question would be but there are few variables which are known not to follow a normal distribution, like a duration of hospital stay. It will never follow a normal distribution because it is usually not normal in distribution. So the median duration of hospital stay of AIIMS Patna is different from AIIMS Delhi. If that is my research question, I will use man with NEU, or a comparison of income of general physician and general surgeon. That could be again a research question, or comparison of CRP level of severe and mild COVID cases. Again, there will be it will be not normally distributed. So in this case, we already know that the variable of interest does not follow a normal distribution as reported in the previous study. So beforehand, we plan to compare the median of the variable of interest. But if, as a policy, if you don't know whether the variable will follow, I mean, you should test the median or mean, you should always start with mean, test for normality. If it is not normal, then you can test for median. Is it okay? So in all these research questions, what we have observed, that the scale variable in the question is a continuous variable, and the second variable, that is a independent variable, is a nominal variable. That too, it is having a two categories. So the choice of the test in all these cases would be to see the test which checks whether any difference in the median value of a scale variable across a binomial variable, So it is the Mann-Whitney test, also known as the Wilcoxon-Mann-Whitney test. So it has got certain characteristics. So what are those characteristics? It is a rank-based non-parametric test, also known as the Wilcoxon-Mann-Whitney test. Here there is a one dependent variable, which is continuous or ordinal. Ordinal in this case would be like pain score, because there are many ordinal variable which has got more than 7 categories. So if an ordinal variable has got more than 7 categories, you can change that to a continuous variable. So that's because the VAS scale, that is a 10-point scale. So you can change this score to a continuous variable, although it is ordinal in nature. So there is a rule that any ordinal category, more than 7 categories, you can change that to a continuous with 1 to 7 score. Then again, one independent variable which will have 2 categories. There should be independence of observation, which we have seen that the one person should be counted only in one group, and the distribution of score for both the group of independent variable should have the same shape. Now, what do I mean by this? Here you can see there are 2 graphs. In the first graph, you can see the distribution of male and female. So first, in the first graph, which is on towards the left side, you can see here that this graph, in both these 2 graphs, it is these 2 are of the same shape. The blue one is for the male and the red one is for the pink. But if you see this graph, the second one, here the shape of male and female, it is different. You can see from the tail of the graph that it is the right skew and this is the left skew. So although distribution in the first case, it is a skewed one, but both has got the same skew. Whereas in the second graph, the distribution is a skewed one, but both has got a different, different angle, or you can say different direction of skew. One is the right skew and the other is the left skew. Similarly, so this was the case. So you should see, we will see how to see these shapes. So the hypothesis in case of a Mann-Whitney is the median of the 2 groups are equal, and the alternate hypothesis is the median of the 2 groups are not equal. That is the alternate hypothesis. So normality testing would be the same. So I think I will not tell you this directly. I'll go before that. I just want to, these are all commands. I want to make one important point here at this point of time about this. So if in case when the distribution of 2 groups are equal, then what should be the comparison? So this Mann-Whitney, we compare 2 things. We compare either the mean rank or we do the comparison of median. So when the distribution of the 2 group is same, like in the first case, we see that there is a skew, but both the groups have got a same skew, either the right skew or the left skew, then the right option would be the comparison of median. But if the distribution of the 2 group is not same, then the right option would be the comparison of mean rank. That we will see in the data set, how to do that. So is that clear to you? The only different assumption here in this case is that you have to see the distribution. So if the distribution of the 2 group, because the data is not normal, we know that the data is not normal, but we have to see the direction of skew. So if the distribution of continuous variable across the 2 category is in the same side of skew, same distribution, we test for a comparison of median. And if the distribution is of different shape, then we compare mean rank. Now, how to do that? We'll see in the data set. So this is the data of Mann-Whitney, and this is the question. So question is like, you want to study whether there is any difference in the mean SGOT level of a patient who have got a first MI and a recurrent MI. So, and the SGOT in LDH, both. So you can apply that. So I'll open this sheet and again, I'll apply that normality. So I'll go to analyze, descriptive, and then explore. In the explore, I have to see the LDH and SGOT. So I'll put this SGOT on LDH in the dependent list and the order of MI in the independent list. Then I'll click here plots. I'll go to plots. I will uncheck this. I will check this normality test with plot. I'll press this continue. Okay. Wait for the result. In the result, you can see just see the, if this we have seen earlier also, the QQ plot of SGOT. So there is a skew. And again, if you see the QQ plot, there are many outliers. If you see the QQ plot of LDH, you can see also it is skewed one. And then this is also a skewed one. And if you see the box plot, it is again, outliers are there. So in this case, what I'll do, that I will go for the non-parametric. I have decided to go for a non-parametric. So the commands for non-parametric, this is a little bit different. So just see it patiently, because we don't go by this compare of mean. Rather, here, if you go, we go, there is an option of non-parametric test. So we go into the non-parametric test and we click on independent sample because it is an independent sample. So click on this independent sample, then these three, this window will appear. So this objective, you don't do anything. It only tells that the automatically compare distribution across group. Yes, because I have to compare between the two groups. So you don't have to do anything in this. You come to the field. If you come to the field, you have to shift your value, these two variables here. So I have pressed control and then you shift these variables here. Then again, across which group? So here you can see, here it is writing, I told you, this is the scale sign of scale variable. And this is the sign of ordinal variable. So I've told you that if the ordinal variable is more than 7 in category, then you can treat it as a continuous variable and you can apply Mann-Whitney test. Similarly, the grouping variable here is the MI order. So I'll shift the MI order here. And then again, I'll come to the third option. So that is the setting. In the setting, I have automatically, it comes automatically choose the test. But no, I want to customize test. So press on this customize, then click on this Mann-Whitney U because it will be the 2 sample test. And then press the option run. Okay. If you press this option of run, then you will have this, this hypothesis test summary. This table will appear, right? So this table tells you about the null hypothesis, about the test, and about the decision. So in this case, it was a rejection of null hypothesis because the significant level is less than 0.05. In the second hypothesis, it is we have retained the null hypothesis because the value is more than 0.05. Now you double click on this table. If you double click on this table, there will be appearance of a model viewer. In this model viewer, the part which is yellow in color, it is showing you the detail of that part. So this right hand side window, this is showing you the Mann-Whitney U test of this SGOT level with first order MI and recurrent order MI. Are you clear with this? All of you, is it clear to all of you?
Yes, ma'am.
So this is important. Now, can you see the distribution? This recurrent order, this is a type of histogram. Can you see this? And this blue is also a type of histogram. although it is vertically appearing, so it may look a little bit different to you, but think of this as a x-axis and think of this as a y-axis. So these are the two parts. Can you see? So if you see the shape of these two, they are almost of having the same direction. So if they are having the same direction, what we plan that we have to report the median. Although you can report mean rank also, if you can report both of them, but you should always report median also. But this command doesn't give you the median value. Okay, this only tells that there is a significant level of SGOT between the first and second order. This tells you the value of Mann-Whitney statistics, and this is the standard error. You have to report the standard Z statistics. This we report, and this is the p-value. So we report standard Z test statistics from here. We report this. We report, just a sec, sorry. We report this, and then we report test statistics, and we report Z statistics too from this, and we say that this Mann-Whitney and test statistics will be the same because it is the value of Mann-Whitney only, and we comment that the distribution of SGOT across the first and second order of MI was same. Okay, so now there is one more command which I need to run. So before I go to that command, let's see this distribution. So if you click this one, again you can see here that it is almost the same, both are having the same shape. So it is again here we can compare the median value and the mean rank also. So can you see the mean rank? It is 91.38, and here the mean rank is 102.78. Okay, so now we have to put the command for median value. So for command of median value, you go back to the SPSS where we have given the command. There you will have to go to this analyze option. Then there is an option of compare means. So you have to come here as a compare mean. Here you have to put the value of SGOT and LDH in this box. And in the independent, you have to put the MI order. If you go to the option here you are seeing that there is a median. So here you should shift all this to this box, back, and shift median to this, and then continue. So in the output, you can see you can see the median value. So the median of first order MI was 47 SGOT, and this is the recurrent order. LDH is 791 and recurrent is 905. So if I have to report this result to a table, then how will I do it? This is the, no, this was not the one, sorry. Yes, so this was the table and interpretation. So I have opened both these sheets simultaneously. The output of this.
Excuse me, Dr. Pragya.
Yeah. Yes, Dr. Mukta.
In this example, the both first and recurrent MI, the SGPT level is differently skewed. एक का tail left में जा रहा था, एक का right में जा रहा था. तो यहाँ पर तो हमको mean compare ही mean rank ही compare करना चाहिए.
आप कर सकते हैं, आप generally recommended है. आप इसलिए अगर जैसे कई बार क्या होता है कि बहुत clear अगर नहीं हो रहा है, so you should give both the thing, mean rank as well as median value. There is no harm in it.
Okay.
At times what happens that it is not very clear from graph. So what we do, we give both the mean rank and the median value as well. So that tells, and you can write in the interpretation, even if you don't write it, you just write that you have given the mean rank. Actually, the interpretation of mean rank is different.
Okay.
Why? Because mean rank, like if there is a hemoglobin level of 16 of a female, the second female is of a 9, the third female is 8, then what this mean rank will do, this will categorize 8 as 1, 9 as 2 and 16 as 3. Although there is a huge difference between 9 and 16, but this ranking में वो क्या करेगा, इसको third rank दे देगा. तो उससे कई बार क्या होता है ना कि जब आप उसको when you tell this ना, तो कॉमनली इससे समझ में नहीं आता है कि मीन रैंक से एक्चुअली कोई क्या इन्फर करेगा. इसलिए मीडियन इररिस्पेक्टिव दे देना चाहिए, बिकॉज एटलीस्ट दैट मीडियन विल टेल यू कि 50th नंबर पे जो आपका है ऑब्जर्वेशन, उसकी वैल्यू क्या थी. ओके
Okay.
सो हियर यू कैन सी how to interpret this. So this is a table, and this is the first and the second order MI, the SGOT level. So I have, you can shift, you can see here. This is the 47 and 59, which is from this table. Statistics, where I have used that statistics, result man Whitney U. So you come here, you double click on this. Okay, actually this will not come. Okay, yes, it will come. If you move this to, there is an arrow here. There's a small arrow here. So if you, just a sec. So now this will appear. So you can see here that the test statistics 3149. I think this by mistake, we have taken the value of LDH. So this is a wrongly written thing. I will show you. Oh no, yes. So by mistake, I clicked that. That's why. Again, this value is, I think we have, this is, I'll correct this. This is 4831. 4831. Z value will be 2.34. And I'll remove this minus sign. And then P value is okay. So can you see this now? This is the interpretation. And if you just see the interpretation, one of you can read this interpretation.
The values of SGOT was not distributed normally across myocardial infarction order as tested by visual inspection of QQ plot. A Mann-Whitney U test was run to determine if there were difference in SGOT level between first order and the recurrent MI cases. Distribution of the SGOT level for first order and the recurrent MI cases was similar as assessed by visual inspection. Median SGOT for first order MI 47 and for recurrent MI 59.5 was statistically significant, with Mann-Whitney U value of 4,831 and Z score of 2.34 and P value of 0.019.
Yes, so this is if you think that the shape, like if you think here that the shape is different, you may write yes, Dr. Mukta was right that it is not exactly the same. So here we have not given the mean rank, but here you can write in this table only. You can enter mean rank along with that, and you can enter mean rank also. Like in this case, the first order will be the 90.68. Let me see which is the first and which is the 7. So first order is 90.68. So you can write here 90.68, and you can write the second value here as 111.02. So similarly, you can enter the mean rank and you can interpret that also.